Another application of the derivative is something that can help us solve limits that before were unsolvable. The question we're going to answer is, how do we take a limit of an indeterminate form? And the way we're going to do that is with what is called L'Hopital's rule. Now, L'Hopital was a French mathematician who published this idea in a French calculus text. However, he's probably not the one who came up with it. It was probably one of the Bernoulli mathematicians. The Bernoullis was a Swiss family that were some of the most amazing mathematicians ever, and they all were from the same family. And there's some evidence that one of the Bernoullis were the first to come up with it, while L'Hopital was the first to publish this rule, or this trick, to take the limit of an indeterminate form. But first, before we can get into what the rule is, let's make sure we understand what the heck is an indeterminate form. There's lots of indeterminate forms. These are things that are technically undefined, but we know that limits often exist at points that are undefined. And one of these, there's actually two really common ones that we're going to use, is when the limit as x goes to some number, we'll call it a, it could also go to infinity, of f of x over g of x, where we've got some fraction. But when we normally do a fraction with a limit, we take the limit of the numerator and the limit of a denominator and simplify what that comes out to. But when that reduces to 0 divided by 0, we say that is an indeterminate form. We don't determine anything. It doesn't necessarily mean it doesn't exist. 0 divided by 0 is indeterminate, so we need to do another strategy in order to solve. The second indeterminate form, a really similar idea, is the limit as x goes to a of f of x divided by g of x. Sometimes will equal infinity over infinity. And it could be either positive or negative over a positive or a negative infinity. But this is also indeterminate because it turns out there are different sizes of infinity. And we don't know if we're dividing by the same size or different size. Is it 0? Is it infinity? Is it 1? It could be lots of different things. So if our limit is one of these indeterminate forms, L'Hopital suggests the way we solve it using his rule. If our limit is an indeterminate form, it can be shown that the limit as x goes to a of that fraction, f of x over g of x, is equal to the same limit as x goes to a, but this time of f prime of x over g prime of x. And often, this second limit is much easier to take. In other words, if we do a division or a fraction with an indeterminate form, we'll just take the derivative of the numerator and the derivative of the denominator and calculate that limit. So let's do some examples where we do just that. First example, we're going to take the limit as x goes to 0 of sine x over x. Now, normally, we'd plug 0 into the numerator, and the sine of 0 is 0. And we plug 0 into the denominator, and that becomes 0. So what we're really saying is 0 over 0, which is an indeterminate form. So what we will do is we will take the limit as x goes to 0 of the derivatives of the top and bottom, the numerator and denominator. The derivative of sine is cosine, and the derivative of x is 1. So we're really saying, let's plug 0 into the cosine of x. So we'd have the cosine of 0 over, the 1 is still 1, and the cosine at 0 is 1. So this limit, as x approaches 0, is actually approaching 1. And that's L'Hopital's rule. Take the derivative of the numerator and the denominator, and take the limit. Let's try another one. Let's do the limit as x goes to 1 of the sine of pi x over the natural log of x. Well, if we plug 1 into both of these, we get 1 times pi, or the sine of pi. In the sine of pi, the y-coordinate there is 0. And the natural log of 1 means e to the 0 power is 1. So we've got 0 over 0. We have an indeterminate form. Because we have the indeterminate form, we can take the derivative of the top and bottom and find that same limit. The derivative of sine pi x is cosine pi x times the derivative of the inside, which is pi, over the derivative of the natural log of x is 1 over x. Well, 1 over x, that is dividing by a fraction. It's the same as multiplying by the reciprocal. So I'm going to simplify this one step further and flip that fraction over. And we have x pi cosine pi x. And now if we plug 1 in, we get 1 times pi times the cosine of pi times 1, or 1 pi. So we have 1 times pi. Cosine of pi, the x-coordinate at pi is -1. So we have 1 times pi times -1, which is negative pi. Our limit as x goes to 1 is negative pi. This even works on problems with infinity that we've seen before. Let's say, remember when we were doing limits at infinity, the limit as x goes to infinity of 3x squared plus 2x minus 1 over 5x squared minus x plus 1. And if you remember before when we were doing limits with infinity, we said, OK, the x squared is going to take over. And so the x squared part gets huge. And then we end up dividing out the x squareds, and we're left with 3/5. But let's solve this using another method, using L'Hopital's rule. Because as x goes to infinity, the numerator becomes infinity squared times 3 plus 2 times infinity. It's going to infinity. Same thing with the denominator. It's going to infinity. We have infinity over infinity, which means we have an indeterminate form. And we can take the derivatives of the numerator and denominator. That gives us 6x plus 2 over 5x minus 1. Nope, 10x minus 1, sorry. But now, if we plug infinity in, we have 6 times infinity, which goes to infinity. And then the denominator, we've got 10 times infinity, which goes to infinity, which means we still have an indeterminate form. But there's no reason we can't use L'Hopital's rule twice. So again, we'll take the derivative. The limit as x goes to infinity. The derivative of the numerator is 6 over the derivative of the denominator is 10. And that's just a constant. It doesn't matter what x is approaching. It's a constant, 6/10, which reduces to 3/5. We can even use L'Hopital's rule with a one-sided limit. Let's say the limit as x goes to 0 from the right of the natural log of x over the cotangent of x. We might need a little bit more room here. Now, as x goes to 0 from the right, the natural log goes to negative infinity. And as cotangent goes to 0, Cotangent goes to 0. Remember, cotangent is cosine over sine. Cosine over sine is actually going to be an asymptote. That guy's going to infinity. We have negative infinity over infinity. We have another indeterminate form, so we'll take the derivative of the numerator and the denominator. The derivative of the natural log is 1 over x. The derivative of cotangent is negative cosecant squared x. And let's actually simplify that. It's negative. 1 over x sticks an x in the denominator. And cosecant is the reciprocal of sine, so let's put the sine squared in the numerator. Whoops, I forgot the limit. That's important. The limit as x goes to 0 from the right of sine squared x negative over x. And now if we plug 0 in, the sine of 0 is 0. Squared is 0. And if we plug 0 in, the denominator now goes to 0. So all we've done is we've gone from indeterminate form infinity over infinity to another indeterminate form, 0 over 0. So L'Hopital says we do it again. The limit as x goes to 0 from the right of the derivative of negative sine, well, the negative stays there. The derivative of sine squared is 2 sine x times the derivative of the inside, which is cosine x, over the derivative of x is 1. Now we can plug 0 in, and we'll actually get a solution. Now we have negative 2 sine of 0 cosine of 0, which is negative 2 times the sine of 0 is 0, the cosine of 0 is 1, and it simplifies down to a limit of 0. So this is the big idea of L'Hopital's rule. If we have infinity over infinity, or 0 over 0, we'll take the derivative of both the numerator and denominator so that we can take the limit and plug it in. We might have to do it several times, but eventually we can get down to a limit. Those are the indeterminate forms that L'Hopital's rule allows us to work with. But there are still other indeterminate forms that you could end up with. The general strategy we're going to imply for these other indeterminate forms is that we need to make them either 0 over 0 or plus or minus infinity over plus or minus infinity. We're going to massage them a little bit to try and make them into an indeterminate form. One classic indeterminate form is 0 times infinity form. What's nice is the reciprocal of 0 is infinity. So we're going to move that 0 to the denominator, and then we'll be in an indeterminate form. Or the reciprocal of infinity is 0. So we could do the reciprocal and move it to the denominator, because dividing by a reciprocal is the same as multiplying. And we'll end up with a form we can work with. Here's what this looks like. The limit as x goes to 0 of x squared of the natural log of x. Now x squared, that's going to 0. But the natural log of 0, natural log is approaching negative infinity. So we've really got 0 times negative infinity. So we're going to rewrite this problem, moving one piece down to the denominator as a reciprocal. So let's move the x squared down here. So we'll have the limit as x goes to 0 of the natural log of x over x to the negative 2, or the reciprocal. X to the negative 2 would move that exponent up. So you can see these are equivalent expressions. But now what we have is the natural log of x still approaching negative infinity. And x to the negative 2, or 1 over x squared, is approaching infinity. And the reason that's going to 0 is we have 1 divided by a teeny tiny number. And when we divide by a teeny tiny number, we get a huge number as a result. So now we have the correct indeterminate form. We're ready to use L'Hopital's rule. And we have the limit as x goes to 0 of the derivative of the numerator, which is 1 over x, over the derivative of the denominator, which is negative 2, x to the negative 3. Cleaning that up a little bit, the negative 2 is going to stay in the denominator. We still have the limit as x goes to 0. Leave the negative 2 in the denominator, but the x to the negative 3 moves up. And the 1 over x means it needs to move down. And actually, that can clean up a little bit. We have the limit as x goes to 0 of x squared over negative 2. And now we're ready to plug 0 in for the x. And when we plug 0 in for the x, we get 0 squared divided by negative 2, which is just 0. So how we handle that 0 times infinity form is we move one piece to the denominator using its reciprocal. It's still equivalent that way, and then we're in that indeterminate form that we can use L'Hopital's rule on. Another indeterminate form is when we have infinity minus infinity. If we have infinity minus infinity, we need to find a way to combine these to get a single fraction. An example of this would be the limit as x goes to 0 from the right of 1 over x squared minus 1 over sine of x. If we were to plug 0 in, we would have 1 over 0, which is infinity. And the sine of 0 is 0, so we have 1 over 0, which is infinity. And so we end up with infinity minus infinity, which is not necessarily 0 because they might be different sizes of infinity. So this is indeterminate form. So we need to combine them into a single fraction so that we can try and use L'Hopital's rule if we do, in fact, have an indeterminate form. Common denominator would mean we multiply the first fraction by sine x over x, and the second fraction by x squared over x squared. And that's going to give us sine x minus x squared. Whoops, forgot the limit part. That's important. The limit, as x approaches 0 from the right, of sine x minus x squared over x squared times sine x. Now you'll see if we plug 0 into the numerator, the sine of 0 is 0. Minus 0 squared is 0. And in the denominator, we multiply 0 times 0 to get 0. We have an indeterminate form which we can use. So now we have the limit as x goes to 0 from the right of the derivative of sine is cosine x minus 2x over 2x times sine x using our product rule plus x squared times negative cosine x. So I'll make it, oops, sorry, not negative cosine x. Derivative of sine is positive cosine. So we have x squared times cosine x. Now we have something that we can take the limit as x goes to 0 on. Let's break this down piece by piece so we can really see what's happening. When we plug 0 into the cosine cosine of 0 is 1, minus, actually let's just hit equals. The cosine of 0 is 1 minus 2 times 0 over 2 times 0 sine of 0 minus 0 squared times the cosine of 0. Well, we still are ending up with 0 in the denominator, or we're getting closer and closer to 0 from the right, because we end up with 0 minus 0 in the denominator. But as we get closer and closer to 0 from the right, what that really means we're doing is we have left in the numerator is 1 minus 0, divided by something that is almost 0, because we're getting closer to 0 from the right. 1 divided by almost 0, or 1 divided by something really, really small. When we divide by tiny, 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 tiny things, we end up with huge answers. And so this limit, as x goes to 0 from the right, is going to be a positive infinity. Let's try another one. Another indeterminate form is when we have infinity to the 0 power. It's not necessarily 1. Might be 1, but not necessarily. For these, we're going to use logarithmic substitution to help us out to solve these problems. If we have the limit as x goes to infinity of x to the 1 over x, you'll notice the exponent, 1 over infinity, is going to 0. And the base, infinity, is going to infinity. We have infinity to the 0 power. So we're going to rewrite it. Using logarithmic substitution, we're going to let y equal the stuff we're taking the limit of, 1 over the x. Natural log of both sides moves the exponent out front. And we're going to take the limit of what we ended up with and know we can undo that natural log by taking e to whatever power we end up with as our limit or our solution. So we're going to take the limit as x goes to infinity of, and we're going to write it as a fraction, natural log of x over x. Because we know that natural log, as x goes to infinity, also goes to infinity. And so we now have infinity over infinity. We can now use L'Hopital's rule. The limit as x goes to infinity of 1 over x over 1, which, if we clean it up, is the limit as x goes to infinity, moving that x to the denominator of 1 over x. Which we know we're doing 1 divided by infinity, or 1 divided by a huge number. And when we divide by a huge number, you're just left with 0. But that is the limit of our natural log. We have to undo the unnatural log by taking e to that power. E to the natural log of y is y, so e to the 0, and I'll make a note here to undo the natural log that we did. The opposite of taking a natural log is e to the exponent. We take that solution we had as our exponent, and e to the 0 is 1. So our limit, as x goes to infinity, of x to the 1 over x is equal to 1. Let's try another one where we use that strategy again, where we take the natural log of y in order to help us solve. This one turns out to be in the 0 to the 0 form. which is also indeterminate because a base of 0 should have a 0 for a solution, but an exponent of 0 should have 1 for a solution. So what is the solution? Well, it depends. Let's take the limit as x goes to 0 from the right of x to the sine of x power. Again, you'll notice if we plug 0 into the sine of x, the sine of 0 is 0. And then we have a base of 0, so 0 to the 0 power is indeterminate. So we let y equal x sine of x. And then we take the natural log of y, which moves the exponent out front. So we have sine of x times the natural log of x. Now again, we're going to get rid of that natural log by taking e to our exponent. So we're going to actually calculate the limit as x goes to 0 from the right of sine x times the natural log of x. The problem is, as sine goes to 0, as x goes to 0, sine goes to 0. And as natural log goes to 0, it goes to negative infinity. We've got 0 times negative infinity. We've done this form before. This was number 1, where we said we're going to move a reciprocal down into the denominator. Let's use that exact same strategy here. We could move either one. There is one that actually turns out to be easier and better. I'm going to come down on the next line to give me some space. Let's move the sine of x into the denominator. So the limit as x goes to 0 from the right of the natural log of x over the sine 1 over the sine of x. It has to be the reciprocal when we move it down. And actually, what's nice is we know the reciprocal of the sine function is the cosecant. So we're really doing the natural log of x over the cosecant of x, which means now we've got the natural log as x goes to 0, the natural log goes to negative infinity. And for the cosecant, as x goes to 0, cosecant goes to positive infinity. We have an indeterminate form that we can finally use L'Hopital's rule on. So now we have the limit as x goes to 0 from the right of the derivatives. 1 over x over the derivative of cosecant is negative cosecant cotangent. And let's clean that up. The limit as x goes to 0 from the right. The 1 over x moves the x down. Cosecant and cotangent are both very familiar reciprocal functions, which will move them up, which will be very nice. Cosecant is the reciprocal of sine, so negative sine x. And cotangent is the reciprocal of tangent, so negative sine x over x, tangent of x. Let's keep cleaning this up. I want to break this up into two pieces. Let's break this up into the limit as x goes to 0 from the right of the negative sine x over x times the tangent of x. Because what's interesting there is we know we can use our limit properties to break that up into the product. The limit as x goes to 0 from the right of negative sine x over x times the limit as x goes to 0 from the right of the tangent of x. And why would that be better? Well, if you remember at the very start of our discussion, we solved the limit as x goes to 0 of sine x over x. We know that's equal to 1. So coming down to our problem, we have that same limit. We just have a negative sign, which can come out front. So if sine x over x is 1, negative sine x over x is negative 1. Times, plugging 0 into tangent x. Tangent is sine over cosine. Sine of 0 is 0, so we have 0 over 1, which is 0, which means negative 1 times 0. We've got our limit at 0. But let's not get too excited, because remember, we did that natural log substitution. So we have to undo that natural log substitution by just taking e raised to our solution. Our solution was 0. E to the 0 is 1. And so we ended up with 1 for our solution. So that's L'Hopital's rule. L'Hopital's rule says we can take the derivative of the numerator and denominator if we have an indeterminate form, like 0 over 0 or infinity over infinity at the limit. However, if it's not in one of those indeterminate forms, we're going to have to massage the problem a little bit to put it into a useful indeterminate form. We might do that by moving a piece to the denominator. We might do that by combining fractions into 1. Or we might do that with logarithmic substitution. Take a look at these, give them a good practice, and we will discuss them more in class.